We already discussed creep strain, which is increase in strain at constant stress. And so the stress is constant as you see here, and the strain builds up. And that's the more common version, which I discussed earlier. And this is less common. Strain is kept constant, but the stress, this is the constant strain, stress relaxes. And this is less common. Why? Because you can't easily control strain. What you can control is stress. Then you observe strain. And we've pretty much covered all of this, right? So this is what linear elasticity, right? Stress strain constant and is reversible. The path up same as the path down. Then you get to a point where it's no more recoverable and you have permanent deformations. And if the stress is constant and strain increases, what you have is perfect plasticity. If you need higher values of stress to get more strain and the material is appearing harder, then it's strain hardening. And the opposite, where you need less stress to produce more strain, is strain softening. And these three are viscoelasticity or viscoplasticity if it's not reversible. And this will be the high viscosity, right? At higher viscosity, you need higher values of stresses to produce the same strain. So that's your viscoplasticity, and that's your other forms of plasticity. These are some of the ideal conceptual models for viscoelasticity. So there are many, not just one. And we've discussed a few of those. We discussed this before within the context of poroelasticity, where you have Hooke's law spring in connection with a damper or dashboard, and that is controlled by the viscosity. A different model, void solid damper in parallel with Hooke's law spring, and there are different expressions for those. So all these models have a mathematical expression, that is the one for the standard linear solid, and you can use any of those to fit your data. But the question is, which of them will give the best predictive, will be the best predictive model in terms of the long-term behavior of your rock? So it's easy to match any of these models to experimental data, which is usually a short-term data, right? But you want to predict how the subsurface will deform over tens of years, and that's the challenge. And again, like I said, these models are analytical models. They can be solved easily. They have analytical solutions. You can fit several of them. Which one gives the best long-term prediction? That's what you want. So we need to be able to come up with measurements in the lab that could be representative of long-term subsurface behavior. And that will require thinking about the laboratory setup and design. And then we can now try the different constitutive models and figure out the one that best predict the long-term behavior, not just a short-term data set. And in pages 78 to 83, there is a discussion of that approach. So these, the blues, are data points from a laboratory experiment, and the red is a viscoelastic model. Again, these are even more viscoelastic models that you can use, and you can see all of them have that curve, right, which is indicative of viscoelasticity, except this. So this data has been fitted, if you check out the reference text, has been fitted with almost all of these models. There's also the power law model. But again, we'll need to think about the design of a lab experiment that will give long-term data so that you can be sure your model is not just matching lab data, but is representative of long-term geomechanical deformation in your petroleum reservoir. Now we turn onto the mineral composition of your shale rocks. So these are different shale samples. Barnett dark, Barnett light, Haynesville dark, Evans dark, Eagleford dark, Eagleford light, and the Fort John. What's the difference between the dark and the light? The dark, which is actually darker in color, but contains more organic material. So that's the main hallmark of the dark, and you can see that in the TOC, total organic carbon content, in weight percent. You see the dark is more than the light. The dark has more organic carbon content than the light. And the organic carbon is actually a weak material, pretty much like clay. So more of clay, more of TOC in weight percent gives a weaker material. And so you will have more creep when you have high clay content, high TOC content. These materials are actually tough. So QFP is quartz, feldspars, which is iron-based, and pyrites. Unlike all other experimental results shown previously, which were from consolidated sands, the results that you will be seeing in the next module are based on these, and these are actual consolidated shales. So they have high stiffness and they have high compressive strength, and you still see creep behavior because they have lots of clay, consolidated clay though, and TOC, but the material still creeps. So clay content, TOC content increase creep behavior, not just in unconsolidated sands, but even in consolidated shales. And these shales have very low matrix permeability, which is characteristic of unconventional oil and gas reservoirs. Low matrix permeability, low porosity, and already explained the meaning of TOC and QFP right here. So these data sets, these samples will be used in the experiments we'll be talking about in the next couple slides. And they are all shales, right? Organic rich shales.